So I'm going to go through this video and walk through how we're going to calculate a chi-square test for independence. Now, first of all, the reason why we would use this chi-square test for independence is because these numbers are just frequencies. These are just frequencies. If you'll notice here, it says Mr. Conway obtains a sample of 40 children from other teachers' classrooms at his school, and through home observation, he categorizes each child as receiving unconditional positive regard, frequently, sometimes, or rarely. So he basically is just observation and putting the children into categories. So there's 40 children total. So if you were to add up, 12 plus 3 plus 7 plus 6 plus 9 plus 3, that would be your 40. So it's just frequencies. Now we have two different variables. We have the behavior, and we have basically unconditional positive regard. So the category for the categories are within that independent variable. So we have three categories, or three cells, or three levels of unconditional positive regard, and we have two levels for behavior or problem behavior. So ultimately, we'll start out getting our alternative hypothesis. And I use UPR as a notation for unconditional positive regard. It's a frequently used. So UPR, unconditional positive regard, is significantly related to child behavior problems. So it's either a problem or not. So we'll put behavior problem. Because really, ultimately, that's what the chi-square test for independence does, is it looks at a relationship between those two variables. So now is what we can do is move forward and get our critical value. So our test for independence is going to use the degrees of freedom K1 minus 1 times K2 minus 1. Basically K meaning the categories in the first independent variable times the categories in the second independent variable. So it ends up being, here we have 1, 2, 3. So 1, 2, 3, right? Categories for unconditional positive regard. So 3 minus 1 times, now for behavior we just have two categories, behavior problem or not a behavior problem. So 2 minus 1. So it ends up being 2 times 1, right? So our degrees of freedom ends up being 2. So then we're going to look up our critical value in the back of the textbook. Right here it says we're going to use 0.05. So if you look up 0.05 in the back of the textbook using degrees of freedom of 2, you should find a critical value of chi-square of 5.99. So basically it's significant if it falls beyond that. So here is the 5.99. Anything out here is significant. So I'll put CV. Okay, So anything out here is significant. So now we've got what we need, basically, for starting our calculations of chi-square. So I'm going to go ahead and forward. So here's our chi-square information. So what we need to do is get our frequencies for our rows. So I'll put here f of r's and f of c's, basically, frequency of columns. And let me erase this little mark. Okay. And what we're going to do is we're going to add up the frequencies. So for this first top row, for the frequently receives unconditionally positive regard, we're going to add up 3 plus 12. So those are the observed frequencies. So we end up with 15. And then in the next row, the sometimes row, we're going to do 7 plus 6. And we get a frequency of 13. And then in the rarely, we're going to add up the 9 plus 3, which is 12. Now, if you'll notice, 15 plus 13 plus 12 is 40, right? So we know we've got those ones accurate. Now we're going to get the frequencies for the columns. So for the behavior problems, it's 3 plus 7 plus 9 is 19. And then for the not a behavior problem, it's 12 plus 6 plus 3, which is 21. If you add up 19 plus 21, you should also get 40. So now we have our frequency rows and columns. So we can use those to get our expected frequencies. So remember, f of e is the frequency of the row times the frequency of the column, all divided by n. So what I do often is I number things. So here's cell 1, here's cell 2, sorry about that, here's cell 3, here's cell 4, 5, and cell 6. So that just keeps me nice and organized. So for cell 1, I'm going to do 2, 3, 4, 5, and 6. Okay? So for cell 1, we're going to do basically, because we're going to line it up. Here's the cell 1, here's the column, and here's the row. So it ends up being, it doesn't matter which order, it ends up being 19 times 15 divided by 40. Okay? That's the f of e. And then the f of e for cell 2 is 21 times 15 divided by 40. And then for cell 3, we have 19 times 13, because we're in that second row, divided by 40, sorry. 19 times 13 divided by 40. And then for cell 4, it's 21 times 13 divided by 40. And then for cell 5, it is 19 times 12 divided by 40. And then cell 6, sorry, I'm running out of room. For cell 6, it's 21 times 12 divided by 40. Sorry, it was really sloppy. So, if you were to calculate those out for cell 1, this is 7 point, and I'm going to round a few decimals, 125. For cell 2, it's 7.875. For cell 3, it's 6.175. For cell 4, it's 6.825. Cell 5 is 5.7, and cell 6 is 6.3. Okay, so now we have our observed frequencies for each of, or our expected frequencies for each of our observed frequencies. So now we can actually start calculating the actual chi-square. So forward, because what I did is I wrote those expected frequencies that correspond with each of those cells, so we can think of our entire chi-square, so f of O minus f of E total, or difference squared divided by f of E. So remember, we're going to have basically 6 little chi-squares we're going to be adding up together because we have 6 cells. So our first, we'll start here, is 3 minus 7.125 squared divided by 7.125 plus, for cell 2, we have 12 minus 7.875 squared divided by 7.875 plus, now we'll go to cell 3, 7 minus 6.175 squared divided by 6.175. Sorry, this is messy. I'm going to keep going down here, plus, now we're going to cell 4, 6, the observed, minus the expected, 6.825 squared divided by 6.825. And then now we can go on to cell 5, which is 9 minus 5.7. This is very sloppy, but hopefully you get the point. Divided by 5.7 plus, and now the last cell 6 is 3 minus 6.3 squared divided by 6.3. So what I end up doing is I usually do each fraction separately, and I have the decimals out to 3 or 4 places, rounding appropriately. So I ended up, when I calculated these out, for this first cell 1, it was 2.388 plus, then the second cell was 2.1607. And what I mean by cell is like the chi-square equation that's calculated for each cell. So like this 2.167, I'll kind of highlight here, this one is this equation. So I'm calling that a cell, basically, the calculation for that cell, because that corresponds to this cell right here. Hopefully that makes sense, just in case it doesn't. So now for the third, I have 0.1102 plus, and now 0.0997. Then for cell 5, I have plus 1.9105. And then cell 6, I had 1.7286. So my total ended up being 8.40. That was my total chi-square once I added all those up. Now, if you recall, our original criteria, we had 5.99 was our boundary. That was the chi-square critical value. So anything out here is significant. If you notice, this would fall way over here. So this is significant, right? So now is what we need to do is, before we write our results, is calculate our effect size. And since this is a 2 by 3, we are going to use a Kramer's V, because the only time you would use a phi coefficient is if it was a 2 by 2. So I'm going to go right to a new page. Our chi-square is 8.40. Our sample size here is n equals 40. That's our total. It fell within this region over here. It is significant. Our Kramer's V is the chi-square divided by the sample size times the smallest of the 2 degrees of freedom. And then all of that in parentheses. So we end up with, if you look back, 8.40 divided by, again, so 40. And remember, this was a 2 by 3, right? So our lowest degree of freedom is 1. 2 minus 1. So it's just 1. It's not a big deal. All of that under a square root. And is what we end up with is, I'll round it, 2.46. So then we have to write our results. Well, remember we did say it was significant. Remember, we can state, chi-square showed, and sometimes you just say chi-square test for independence, but I'm okay if you shorten it, showed, and I'm going to do the unconditional positive regard acronym again, is related to child behavior problems, because it's just like what we had put in our alternative hypothesis as, and now we have chi-square parenthesis, sorry, that was a very messy chi-square, 2, because that's our degrees of freedom that we use to look up our critical boundary, n equals 40, right? And I'm going to put equals down here, 8.40, and then p, comma, p is less than 0.05 because that was our alpha level, and then we're going to give our effect size with v equals 0.46. And those are our APA results. And remember, on the exam, those are worth 20 points each. So not only do you have to have your calculations right so that you can have your test statistic right, but you also need to be able to determine whether it's significant or not, and you also have to have your effect size and whether p is less than or greater. All of this has to be included in this order. So it's basically that APA result is showing me not only can you calculate the information correctly and get the right answers, but are you able to determine whether something is significant or not and then report it in an APA format. So that was chi-square test for independence. Hopefully that was helpful.